Hey, welcome back. In this video, we're going to continue discussing applications of Turan extremal functions. In the last video, we saw an application of the Turan number of complete bipartite graphs, which is known as the Kovari-Sos-Turan theorem, the upper bound on it at least. And we used that upper bound to get an upper bound on the maximum number of unit distances among endpoints in the plane and among endpoints in three-dimensional space. And the technique we used, we took those endpoints, we turned them into a graph, and then we showed that the graph that we built had to avoid some certain complete bipartite graphs. And in this result that we're going to look at in this video, this result's about combinatorial number theory. So it's a different kind of problem than the combinatorial geometry problem we're looking at. But our strategy is going to be very similar. We're going to take the structure that we have in this problem and we're going to turn it into a graph. And we're going to try to show that that graph avoids a certain complete bipartite graph. So before we go any further, let's look at the claim that we're going to try to prove in this video. And the proof of this claim is going to be a lot more involved than the proofs that we saw last time. So the proof's going to be a little longer and we're going to have a little more tools to use in it. So the claim in this result is that we have some subset of the integers. We call the subset A. And we define this structure right here. We've never seen this before. This is known as a sum set. So if you have a set of real numbers, you can define sum sets. You can define a sum set of a set with itself, and that's what we're doing here. We're doing A plus A. Now, what does it mean to take the sum set A plus A? All we're doing is we're taking the set of all values, which can be expressed as a sum of a little a plus a little a prime, which are both elements of big A. So any number that can be expressed as a sum of elements of big A goes into the sum set A plus A. And our assumption for this claim, the hypothesis, is that given this subset A of the integers, the sum set A plus A must contain the first n positive squares. So that's our assumption. The first n positive squares, 1 squared, 2 squared, up to n squared, these are all elements of the sum set A plus A. And we want to use that to prove that the cardinality of A must be at least n to the 2/3 minus little o of 1. I just want to point out here that little o of 1, it goes to 0 as n goes to infinity. So if we wanted to prove this right here by contradiction, we could suppose that the conclusion that we're trying to arrive at is false. So we can suppose that A is too small. We could say A is less than or equal to n to the 2/3 minus some constant. We'll call the constant epsilon. And this is for some constant epsilon greater than 0. So that would be our assumption if we're trying to do a proof by contradiction. And we would try to use, based on that assumption, we would try to use it to show that the sum set A plus A could not possibly contain these first n positive squares. In order to show that that would be impossible, we're going to use the Kovari-Sos-Turan theorem, just like we used in the last video. But this time, we're going to use a slightly more precise statement of the Kovari-Sos-Turan theorem so that we can apply it to complete bipartite graphs whose parts might have dependence on n. So we're going to use a slightly more precise statement of the Kovari-Sos-Turan theorem. The proof of the statement is the same as the proof that I showed in the earlier video. So when I proved the Kovari-Sos-Turan theorem using Jensen's inequality, I showed in that video that Ex of n comma k sub r comma s is equal to big O of n to the 2 minus 1 over r. And by symmetry, we also get an upper bound of big O of n to the 2 minus 1 over s. I just want to note here, I'm not saying that the big O of n to the 2 minus 1 over r equals big O of n to the 2 minus 1 over s. I'm saying that the extremal function is big O of n to the 2 minus 1 over s. So the extremal function is big O of n to the 2 minus 1 over r and big O of n to the 2 minus 1 over s. And this is for constant r and s. So when r and s are constants, we get this bound. I claim we can state the Kovari-Sos-Turan theorem a slightly more precise way when r and s are not necessarily constants. So let's look at this more precise version and see what the difference is with the version of there. So I'm going to circle these 3 parts of it. Okay, the first part to talk about down here, this middle term, the n to the 2 minus 1 over r, that's exactly what we're seeing up here. So that's the part that shouldn't surprise us. We also have these extra terms that we don't see up there. We have the s to the 1 over r, we have the rn. Now, let's consider for a second what happens when r and s are constant. When r and s are constant, this s to the 1 over r right here, this is constant if r and s are constant. So when r and s are constant, that s to the 1 over r term would get absorbed into the big O if they're constant. This rn term right here, rn is clearly big O of n to the 2 minus 1 over r for constant r. So the term s to the 1 over r and the term rn, when both r and s are constants, neither of these terms increases the order of n in the bound. So we still get a bound of n to the 2 minus 1 over r when r and s are constant. So this bound right here, it's not saying anything different than the bound up here when r and s are constant. When r and s are constant, we lose those extra terms, the s to the 1 over r, the rn, because a big O bound is only saying that the bound is true up to a constant factor. So we can just absorb the rn and the s to the 1 over r into the big O. We're still just getting a multiple of n to the 2 minus 1 over r as an upper bound. So I leave the more precise statement of the Kovari-Sos-Turan theorem as a problem for you to think about. And like I said, you can still use the exact same proof we used in the video with Jansen's inequality. You just have to be slightly more careful about keeping track of the coefficients of the powers of n. Besides this slightly more precise statement of the Kovari-Sos-Turan theorem, another tool that we're going to use to prove this result is a famous fact about the divisor function. So let's briefly talk about what is the divisor function. We'll call it d of n, and d of n will be the number of positive divisors of the integer n. So it might help to look at a few examples. So let's consider n and d of n right here. Make a little table. Consider a few values of n, like 1, 2, 3, 4. So when n equals 1, we want to look at the number of positive divisors of n. If n's 1, there's only one positive divisor, just 1. So the number of them is 1. When n equals 2, we can look for positive divisors. We just get 1 and 2. And the number of positive divisors is just 2. N equals 3. This one's kind of like 2. We only get 2 positive divisors, just 1 and 3. So we get 2 for that one as well. Let's look at n equals 4. N equals 4, we can count our positive divisors. We can find 1, we can find 2, we can find 4. There's 3 of them, so we get g of n is 3. What if we have, in general, n is just any prime number? So prime numbers, recall, their only divisors are 1 and themselves, and they're not equal to 1. So primes, they always have 2 positive divisors for any prime. So let's consider one more example. Say n equals 12. So when n equals 12, we can list out the divisors. There's a bunch of them. So we have 1, 2, 3, 4, 6, and 12. So we get a total of 6 of them. And that's enough for examples of d of n. So the well-known fact that we're going to use here, and this fact has been known for a long time, is an upper bound on d of n in terms of n. And this upper bound is of the form n to the little o of 1. Just to emphasize, little o of 1, again, I'm just going to mention, it goes to 0 as n goes to infinity. So that exponent of the n, it goes to 0 as n goes to infinity. Another way we can state this bound is that for every epsilon greater than 0, there exists c sub epsilon with the divisor function of n less than c sub epsilon times n to the epsilon. So the c sub epsilon right here, it's just a constant. It only depends on epsilon. So we're saying there exists some constant depending on epsilon for which the divisor function of n is less than that constant times n to the epsilon, regardless of what epsilon is, as long as it's greater than 0. So even if epsilon is like 0.00001, we can still find a constant for which d of n is less than the constant times n to the epsilon. So we're going to try to use this fact, and we're going to try to combine it with the more precise version of the Kovari-Sos-Turan theorem. And hopefully it'll give us this claim that we're looking for. So this claim, just to review what we're going to try to prove here. Our assumption is that we have this subset A of the integers, and the sum set A plus A right here, we're assuming that it contains the first n positive squares. So that's our assumption, that this sum set must contain the first n positive squares. And we're going to try to use that to prove that the cardinality of A must be at least n to the 2/3 minus little o of 1. And like I said, we're going to try to do this with a proof by contradiction. So in order to do a proof by contradiction, we'll assume that the cardinality of A is too small. So we'll suppose that the cardinality of A is less than or equal to n to the 2/3 minus epsilon, for some constant epsilon that's greater than 0. So that would be contradicting that A is greater than or equal to n to the 2/3 minus little o of 1. Because little o of 1 goes to 0 as n goes to infinity. So little o of 1 eventually is smaller than epsilon. So this would be a contradiction. And we're assuming a contradiction of our conclusion in order to get a contradiction to show that our conclusion is true. So we're contradicting our conclusion in order to derive a contradiction to show that that conclusion is true. And we're going to use the same strategy pretty much that we used for the problem with unit distances. So the general strategy there, we took our problem, we built a graph, we showed that it avoids a complete bipartite graph. Same idea here, it's just the way we build the graph is going to be a little bit different. So first, let's think about that unit distance problem. When we built the graph, we built it with the set of points as our vertex set. In this problem, we don't have any points, but we do have the set A, which consists of a bunch of integers. So it would make sense here to make A the vertex set. So that's what we'll do. And now we have to build the edges. In our graph G that we're building, we're only going to have at most n edges. Each of the edges is going to correspond to some square right here. So you see these squares, 1 squared, 2 squared, up to n squared. Each of these squares, we're going to try to make an edge. Some of them we will fail to get an edge, but most of them will get an edge. And let's see how we'll make the edges. So we're going to look at each x with x equals 1 up to n. So the square roots, the positive square roots of these squares, that's the x's that we're looking at. So x equals 1 up to n. And for each of those x values, we know that the square of x is an element of the sum set A plus A. So we know that there must exist some little a and some little a prime, which sum up to x squared. And this has to be true for all of the x's from 1 up to n, because that sum set, A plus A up here, contains all those first n positive squares. So for each x from 1 up to n, we can choose some pair, A and A prime, which add up to x squared. It's possible there will be multiple pairs. We'll choose exactly 1. So I'm going to write that word exactly above just to emphasize. So we're only going to have at most n edges, because we're only going to choose exactly 1 pair, which add up to x squared. The thing is, we'll only put an edge between a and a prime in this graph G if a does not equal a prime. So it's possible that when we're looking for these pairs, a prime, that add up to x squared, we might only find a pair that has two elements which are the same. So a problem that we could run into when we're assigning these edges is that we find some a equals a prime. In other words, x equals a plus a. So we can't put edges on those because that would be giving us a self loop. We don't want to have self loops in a graph. But the good thing is that these problem pairs, when a equals a prime, they can only occur a few times. And let's be more precise what we mean by a few, and I will do that in the next bullet. So I claim the number of times that this can happen, where we get a problem pair a equal a prime, so that x equals a plus a. This can only happen up to cardinality of a times. So if we have x squared, I should write, not x equals a plus a, but x squared equals a plus a, because our equation is the sum has to be the square. So if I have x squared equals a plus a, that means that x squared is equal to twice some little a in my set big A. So that's the exact same thing. X squared equals 2a versus x squared equals a plus a. And the number of possible values of little a for which this can be true, that some square equals twice the little a, that's going to be bounded by the cardinality of big A, because all of these little a are elements of big A. So there's only at most cardinality of big A of these little a. So the number of problem pairs where a equals a prime, this is going to be at most the cardinality of A. So the number of edges that we're going to get is going to be at least n minus the cardinality of A. And so we can use this. So let's see what we have as far as the information so far. So first, we have the number of vertices in our graph. We built our graph with A as the vertex set. And we assume that A has cardinality less than or equal to n to the 2/3 minus epsilon. That was our assumption to do the proof by contradiction. And so we'll say that the number of vertices in G, we'll call it T. That'll be the order of G. And we know by this assumption up here that T must be less than or equal to n to the 2/3 minus epsilon. Now, as I explained in the previous bullet, we only have at most cardinality of A problem pairs, and all the other pairs give us an edge. And we picked one pair for each integer 1 up to n. So each of the integers that are positive square roots of the first n positive squares up here, we chose some pair a prime, which add up to the square x squared. And as long as a and a prime were different, we put an edge between them. And if they weren't different, then we didn't put an edge. But the number of pairs for which we get a and a prime being the same is bounded above by the cardinality of A. So the number of edges we get, just to summarize, is at least n minus the cardinality of A. And we can see n minus the cardinality of A. We have this upper bound. So upper bound, cardinality of A is less than or equal to n to the 2/3 minus epsilon. So we can write n minus the cardinality of A as n minus the low of n. So cardinality of A grows much slower than n. And this is clearly greater than 1/2 n for n sufficiently large. So that's how we get n minus cardinality of A is greater than 1/2 n for n sufficiently large. And the result we're trying to prove is a result with a little o in it. So it's fine to prove this for n sufficiently large. We're only proving this for n sufficiently large. So we can take any lower bound threshold we want on n. And now we need to show that 1/2 n is greater than 1/2 times t to the 3/2 plus epsilon. So we can show that t to the 3/2 plus epsilon is less than n. And let's see how we show that. We're going to show that just by doing a little bit of arithmetic. So we start with the t to the 3/2 plus epsilon. T we know is less than or equal to n to the 2/3 minus epsilon. So I can substitute that. So I get n to the 2/3 minus epsilon raised to the 3/2 plus epsilon. I can write this as n to the 2/3 minus epsilon times 3/2 plus epsilon. And I can simplify this. So I get n to the 1 minus 3/2 epsilon plus 2/3 epsilon minus epsilon squared. And I can see that that's clearly less than n to the 1. So we showed t to the 3/2 plus epsilon is less than n, and that gives us 1/2 times t to the 3/2 plus epsilon is less than 1/2 n. So we get that inequality too. And I claim now we can use the more precise statement of the Kovari-Sos-Turan theorem. So the more precise statement, it told us that, if I write it down here, Ex and KRS, we can write this as big O of S to the 1 over R. I'll write that a little more legibly, 1 over R. And then we get N to the 2 minus 1 over R. And then we get a plus Rn. So that was the version of the Kovari-Sos-Turan theorem that I asked you to prove on the previous slide. And like I said, you can use the exact same proof as the version with constants R and S. But this version applies also when R and S are not necessarily constant. So we're going to try to apply this version for a non-constant S. And we can see if the number of edges in our graph is greater than 1/2 times t to the 3/2 plus epsilon, in this version of the Kovari-Sos-Turan theorem, we can apply this when r equals 2. So we can write k2s equals big O. We can write this as square root of s times n to the 1.5 plus Rn. So r equals 2 here. I could write 2n, but since it's a big O, I can also just write n, because the big O includes constant factors. So a factor of 2, I don't need to write that. So this is the bound we get for r equals 2, and still letting s depend on n. And so we see if we have more edges than this, so if we go over the threshold, where the threshold is of the form square root of s times n to the 1.5 times some constant. If we go over that, then we're going to have a copy of k2s if the number of edges exceeds that. So if we have greater than 1/2 times t to the 3/2 plus epsilon edges, and the number of vertices was t. So in this case, instead of n's, we can think of these as t's. So I can change these n's right here. Might as well change them to t's, not going to hurt anything. So hopefully that's legible. That became a t. This one's also going to become a t. Now it's a t. Same over here. We don't even have to write the one over here, this t, because this t is smaller than a t to 1.5. So it would just get absorbed into the bound. So we can actually just write this bound as big O of square root of s times t to the 1.5. So we see that if we have more than that many edges, we contain a copy of k2s. Now here our square root of s is of the form, it's approximately 1/2 times t to the epsilon. So the number of edges we have is greater than 1/2 times t to the 3/2 plus epsilon. And we can factor that as just t to the 3/2. So this equals t to the 3/2. And that times the square root of s, where the square root of s, I've written it just as 1/2 times t to the epsilon. And we can see then, if we have that many edges, then we must contain a complete bipartite graph where s equals omega of t to the 2 epsilon. So if the square root of s is 1/2 times t to the epsilon, then s itself must be omega of t to the 2 epsilon. just by squaring both sides. So we just took this, squared both sides to give us that. Now, why do I know that t to the 2 epsilon is omega of n to the epsilon? Well, we can note that a graph with t vertices has less than or equal to t choose 2 edges. So the number of edges in our graph we knew was at least 1/2 n. So we know we have at least 1/2 n edges in our graph. And that number of edges must be less than or equal to t choose 2. So that tells us t must equal omega of square root of n. So we know from this statement, the number of edges in a graph with t vertices is less than or equal to t choose 2. So we can say the number of edges has to be 1/2 n is a lower bound on it. So 1/2 n is less than the number of edges, and this has to be less than or equal to t choose 2, which equals big O of t squared. So this statement right here, a graph with t vertices has at most t choose 2 edges. That tells us that n equals big O of t squared. And n equals big O of t squared, that's how we immediately see that t equals omega of square root of n. So since t equals omega of square root of n, then omega of t to the 2 epsilon is just omega of n to the epsilon. And it's not even important that we got an omega of n to the epsilon. It could have been an omega of n to the 0.00001 times epsilon. That would still give us the contradiction we want. But this n to the epsilon is what we get. So that is how we get all these inequalities in this bullet. So this bullet is probably the most work of all the bullets, but I think we just got through it, so we can go on to the next bullet. I have to erase a lot though, unfortunately. Maybe I'll save it and then erase. Okay. And so we're going to use this complete bipartite graph that we just forced in G. So we knew that since G had so many edges, it has to contain this complete bipartite graph with parts of size 2 and s, this k sub 2 comma s. So that tells us we have this complete bipartite graph. We could draw a picture of it. So we have 2 vertices, and then we have s other ones. And we have edges from the 2 vertices up here to all the ones down here. So that's a complete bipartite graph with parts of size 2 and s. Okay, now let's see what this complete bipartite graph represents with respect to the set S. So we have, let's say, 2 elements of S, which will be these vertices up here, the A1 and A2. And then we'll have a bunch of elements from S, B1, B2, up to BS. Let's look at how we form this graph. So we know that the vertices were just elements of A. The edges, though, for each of those positive squares, 1 squared, 2 squared, up to n squared, we found some pair, little a and little a prime, that added up to the square. And if little a did not equal little a prime, we put an edge between them. So we know that all of these edges we have here, like all these edges from A1, A2 to the BIs, all of those represent some sum that adds up to a square. Moreover, for each of the squares, we only chose exactly one pair that added to the square. So each of the squares that we get for these edges is going to be a different square. So we can take all of those sums, A1 plus B1, A2 plus B1, A1 plus B2, A2 plus B2, A1 plus B3, A2 plus B3, and we keep on going all the way down to A1 plus BS and A2 plus BS. I just want to note, like I said here, each of the squares, 1 squared, 2 squared, up to n squared, we chose exactly one pair, little a prime that adds up to the square. So all these edges that we have here, all of these correspond to different squares. So each of these sums here, we have a total of 2 times s sums because we have 2 AIs and we have s BJs. And any combination of an AI and a BJ, we can take the sum. And we know from this graph, the fact that we have a copy of K2S on these vertices A1, A2, and B1, B2 up to BS. We know that there's an edge AI, BJ for every I and J. And that means we know that all of these sums are squares. They're all squares and they're all distinct squares. So all of those sums that I've drawn below, A1 plus B1, A2 plus B2, A1 plus B2, A2 plus B2, all the way up to A1 plus BS and A2 plus BS. All of these are different squares. And so we have a total of 2s squares up there. 2s distinct squares on that list I made. Now, we can use these squares the way we're going to use them. So we can assume, for example, the A1 plus B1, we know that that's some square. We can say it equals x squared. We can also assume A2 plus B1. This is also a square. We know that all of these sums are squares. We'll say that's equal to some y squared. We'll also assume that since we know A1 and A2 are different vertices, we know one of them is greater than the other. So without loss of generality, we can assume A1 is greater than A2. We can just say A1 is the larger of the two of them. And so we can subtract these, subtract both sides, and the b's cancel here, the b1s. We get A1 minus A2 equals x squared minus y squared. We can do the same thing when we have the sums A1 plus B2. That equals some square. And that w squared has to be a different square than the x squared and the y squared. And we can say A2 plus B2 equals z squared. And we can take the difference again. And A1 is greater than A2. We get A1 minus A2 equals w squared minus z squared. And again, I just want to emphasize, all the squares we have on this list up here, all of them are different squares. So we can do this process. We can take a difference, take the difference in s rows. So I drew a table up there. It has 2 columns and s rows. And we can take the difference of the squares in each of the rows. So each of the rows, we have 2 squares. We take the difference of the terms, and we get A1 minus A2. We always get A1 minus A2 as the difference for each row. But we get a different difference of squares for each row. So the first row, we got x squared minus y squared. Those are the squares for this number and this number. The second row, we got w squared minus z squared. So here's our x squared, here's our y squared, here's our w squared, there's our z squared. And we can just keep on going like this for all s of the rows. And that gives us a total of s differences of squares with which we can represent the number A1 minus A2. So there's the assumption that I mentioned before, that A1 is greater than A2. So, and like I just said a sentence ago, the difference A1 minus A2, we can represent this as a difference of squares in at least s different ways, just using this table. So this table, each row of the table gives us one different way to represent A1 minus A2 as a difference of squares. And we can look at what happens when you can represent A1 minus A2 as a difference of squares now. So let's look at it down here. I'll probably end up erasing this, but for now we can look at it. A1 minus A2 equals x squared minus y squared. And we can write that as x minus y times x plus y. And we can do the same thing with the w squared minus z squared. We can say A1 minus A2 equals w squared minus z squared. And we can use our algebra 1 to factor that. W minus z times w plus c. And like I said, we have a total of s ways to do this. So A1 minus A2 equals some difference of squares down here. We can say, like, pick some unusual numbers like p squared and q squared, p squared minus q squared. Hopefully we didn't use those anywhere. And so that would be like p minus q, p plus q. And we have S equations here, all different squares. So all different squares, a total of S equations. We can look at each of these equations, and we can look at the factor. When we factor the difference of squares, we can look at the left factor. We can also assume each square root is positive. So we only care about the squares, like x squared, y squared, w squared, z squared, p squared, q squared. So the x, the y, the w, the z, we'll assume all of these, x, y, w, z, p, q, all of these positive square roots are greater than 0. This assumption just allows us to not have to worry about when x, y, w, z, p, and q are negative. So when they're negative, it's not going to affect anything. All we're doing here is just showing that the fact that we can represent a1 minus a2 as a difference of squares in many ways is going to give us many positive divisors of a1 minus a2. So whether we're using positive xy or negative xy, it's not going to affect that. It's just going to make our argument a little simpler to require the x and y, the w, the z, the p, the q to be positive. So with that assumption, what we're going to do is we're going to look at each of these differences of squares, and we're going to take the left factor. So the difference of the positive square roots. So the x minus y, the w minus z, the p minus q, and so on. And I claim that all of these are distinct. So all of these smaller factors, the difference of the positive square roots, will never get the same one on two different lines. Now, why is that? Well, we can look at what happens if we would get the same one. So we can say x minus y equals w minus z. And that tells us then, so if we did get the same smaller factor on two lines, this would be what would happen. We'd get some line where the difference of the positive square roots, x minus y, is the same as the difference of the positive square roots in the other line, which is w minus z. So I can use this to get a contradiction. So I know a1 minus a2 equals x squared minus y squared. So I can write x minus y times x plus y equals a1 minus a2. And this also equals, like I wrote over on the right, w minus z times w plus z. Now, if we had this true, so this, we're trying to show this is impossible, but if it was true, then we could divide both sides by the x minus y. I divide this side by x minus y. I divide this side by x minus y as well. But x minus y is the same as w minus z, so I can divide by w minus z, same thing. This gives me x plus y equals w plus z. So I have that from dividing both sides. I also have x minus y equals w minus z. I can solve the system of equations now. And that gives me x equals w and y equals z. So x and y versus w and z, they're just the same. It's the same squares. So x squared would equal w squared, y squared equals z squared. And that would be a contradiction. All the squares have to be different. So we can't have x squared equals w squared. That would be a big problem because we had to have all distinct squares. So this is why we cannot have x minus y equals w minus z. So we can't have that with any pair of the rows. So every pair of rows, they have to have a distinct smaller factor. So the difference of the positive square roots, that's going to be different for each of the rows. So that tells us that since a1 minus a2 can be represented as the difference of squares at least s different ways, that it also must have at least s positive divisors. So now I'm going to erase a lot so that we can see the last few bullets. So this bullet right here pretty much just summarizes what I was writing at the bottom. If we can represent a1 minus a2 as this difference of squares, x squared minus y squared, and like I said, we assume that the positive square roots are greater than 0. It just makes the argument cleaner. Then x minus y, like we saw, is a divisor of a1 minus a2, because x squared minus y squared equals x minus y times x plus y. So x minus y must divide a1 minus a2. And like I explained, there will be no other squares, w squared greater than z squared, for which a1 minus a2 is the difference of squares, w squared minus z squared, and the difference of the positive square roots equals x minus y. So we cannot have this. There are no other squares. So we'll never have the difference of the positive square roots on two different lines of our table giving us the same value. And that's what I just explained before I showed this bullet. So all of these differences of squares for a1 minus a2, each of them gives us a unique positive divisor of a1 minus a2. So in total, we know that there's at least s distinct positive divisors of a1 minus a2. And I wrote down here s equals omega of n to the 2 epsilon over 3. And that's true. So we showed actually s equals omega of n to the epsilon. So this is a weaker statement than what's true. It's still true, but we could have actually stated it a little stronger. So we can write that actually just as s equals omega of n to the epsilon. So we have an even stronger statement than n to the 2/3 epsilon. We can say it's omega of n to the epsilon. Not that it's going to affect the proof at all. So what I wrote here, it's still completely true. It's just, it's weaker than we have to say it, but we don't need anything stronger than that because we already have the contradiction. So we have this many distinct positive divisors, at least s of them. And we know s is omega of n to the epsilon. I just want to emphasize epsilon, that's a constant greater than 0. So we have omega of n to some power, which is a constant greater than 0. Now, we can look at a1 minus a2. a1 minus a2, we'll take the absolute value. So we know in our table, we had this table up here. It was like a1 plus b1, a1 plus b2, all the way down to a1 plus bs, a2 plus bs. And like we said, these were all distinct squares. And moreover, we can look at which squares did we use to build our edges? Which squares did we use to get these sums? It was just the squares 1 squared, 2 squared, up to n squared. So these squares are 1 squared, 2 squared, up to n squared. And so we know when we take the difference, a1 minus a2, that's the same as like a1 plus b1 minus a2 plus b2. This is going to be bounded less than n squared. So we know a1 plus b1 right here. This one must be some element of these squares. It has to be one of those n squares. And same with the a2 plus b2 right here. That also has to be an element of those n squares. None of those n squares exceeds n squared. And also, none of those n squareds is less than 1. So we can say absolute value of a1 minus a2 is clearly going to be less than n squared. So we can't even get n squared for that difference. It has to be strictly less than n squared. And that's how I got this claim right here in the bottom bullet. So it's just from the fact that all the squares that we have in this table, all of them are at most n squared and at least 1. So the difference of 2 of them, its absolute value has to be strictly less than n squared. And since the absolute value of a1 minus a2 is less than n squared, we could say then that d of absolute value of a1 minus a2, we can say that this has an upper bound. So we can write this as big O of the inside to the little o of 1. So a1 minus a2 raised to the little o of 1. And we know that the absolute value of a1 minus a2 is less than n squared. So I can write this as big O of n squared to little o of 1. And when we take n squared to the little o of 1, this is just n to the little o of 1. So we can write this like big O of n to the 2 times little o of 1 if you want. have a little extra step in there. But 2 times the little of 1 is just the little of 1. So like I said, we just get n to the little of 1. So the claim is that the number of positive divisors of a1 minus a2 is n to the little of 1. So it's big O of n to the little of 1. But it's also omega of n to the epsilon. So the same quantity is both omega of n to the epsilon and big O of n to the little of 1. And that cannot happen. You cannot have the same quantity be both big O of n to the little of 1 and omega of n to the epsilon. So that's how we get the contradiction at the end. And that completes the whole proof. So we started with this assumption that A had a cardinality that was too small. We use this with our assumption that the sum set contains the odd positive, or contains the first n positive squares, 1 squared, 2 squared, up to n squared. So we combine that assumption with our assumption about the cardinality of A to show that the graph that we built based on A must contain a large complete bipartite graph. So we took our assumption that the cardinality of A was too small. We took our assumption that the sum set A plus A contains these first n positive squares. And that allowed us to force a copy of this complete bipartite graph and the graph G that we built based on A. So the graph G we built right here, this graph G based on A. And then once we had that complete bipartite graph, we used that complete bipartite graph to force us to have too many positive divisors for this A1 minus A2. So that complete bipartite graph meant that A1 minus A2 had too many positive divisors. The number of positive divisors was the same as the size of the second part in the graph. And we used the fact that we knew about the divisor function, that the number of positive divisors is n to the little o of 1 of the integer n. So the number of positive divisors of the integer n is just n to the little o of 1. So that combined with the number of positive divisors that we got from this complete bipartite graph gave us the contradiction. And that's all we needed, because this was a proof by contradiction. So we just need to get to the contradiction. And that tells us that our assumption about the cardinality of A must have been false. So that completes this proof. So we saw multiple applications of Turan numbers to problems and areas of math that are outside of graph theory. This application was a combinatorial number theory problem. The application we saw in the last video was combinatorial geometry. And that brings us to the end. Thanks for watching.